Explosions, they're just these incredibly powerful, destructive forces. For decades, the only way to really understand them was, well, to actually create them. But what if you could unleash all that power, study every single detail, and learn everything you need to know, all without a single spark? Today, we're going to dive into the science of virtual blast analysis, where all the destruction happens safely right inside a computer. And that's really the big question, isn't it? How can an engineer be sure that a bridge or a building or even a soldier's helmet is going to stand up to a blast? For the longest time, the only way was through physical testing, which, as you can imagine, is not only incredibly dangerous, but also just staggeringly expensive. So what's the alternative? Okay, so let's put these two side by side. On one hand, you've got physical testing. It is inherently dangerous, it costs an absolute fortune for every single test, and you only get one shot at it. If a sensor breaks or something goes wrong, that data is just gone, forever. But on the other hand, you have numerical simulation. It's totally safe, it's way, way cheaper, and you can run the same explosion 1,000 times, changing little things each time to see what happens. You get this complete detailed picture of every force, on every little piece, at every single microsecond. Suddenly, the choice becomes a bit of a no-brainer, right? All right, so here's our roadmap for this explainer. We're going to start with the why, simulating destruction safely. Then we'll take a peek inside the digital lab itself. We'll do a crucial reality check to see how virtual compares to real. After that, we'll look at the incredible real-world applications, from bridges to brains. And finally, we'll see how AI is making all of this smarter and faster than ever before. So let's start with that big shift. This is about so much more than just convenience. It's about moving away from a world of extreme risk and very limited data. It's about creating this digital sandbox where engineers can safely push things to their absolute limit, explore the most extreme worst-case scenarios, and get a level of detailed information that would be physically impossible to capture in the real world. So welcome to the Digital Blast Lab. Here, instead of hard hats and steel-toed boots, the building blocks are all data and algorithms. So what's actually in the toolbox for a computational blast engineer? Let's take a look. Now, these are not the kind of apps you download on your phone. Names like LS-DYNA, Abacus, and Autodyne, these are the heavy machinery of the simulation world. They're incredibly powerful, highly specialized software suites, each one built to solve ridiculously complex physics problems. Think of them as the big guns of virtual engineering. Now, the engine running behind a lot of this is a method called finite element analysis, or FEA. The best way to think about it is like this. Imagine you're building a bridge out of millions of tiny digital Lego bricks. FEA is the magic that calculates how a force, like a shockwave, affects every single one of those tiny bricks, and crucially, how each brick affects all of its neighbors. So how does it actually work? Well, it's a pretty neat three-step process. First, engineers create a perfect 3D digital blueprint of the object. Then, the software slices that model up into a mesh made of thousands or even millions of those little elements we just talked about. And finally, they unleash the virtual blast. The computer then goes to work, calculating the stress, the strain, and the movement for every single one of those pieces. What you get is this incredibly high-definition movie of the entire event. But, FEA is really good at solids, but it's not the whole story. To get the full picture, you also have to simulate the blast wave itself, the air and gas moving at supersonic speeds. That's where something called computational fluid dynamics, or CFD, comes in. And for even messier stuff, like things deforming or shattering into pieces, engineers pull out even more specialized tools like CEL and SPH. It's a whole toolkit, with each tool designed for a specific piece of this super complex puzzle. Okay, this all sounds amazing, right? But it brings up maybe the most important question of all. How do we know the computer is actually right? How can we really trust a simulation when actual lives and critical infrastructure are on the line? You'll see this phrase, or something like it, over and over again in the research papers. Good agreement with the experimental results. Now, that isn't just some throwaway line. That is the absolute gold standard. It's the whole point of the exercise. That moment when the digital simulation proves that it can accurately mirror reality. And that gets to the absolute core of it all. These simulations aren't just built in a digital vacuum. The process is called validation. Researchers take the hard data from those expensive real-world tests, and they painstakingly compare it point by point against the simulation's predictions. The simulation basically has to prove itself against the real deal before anyone trusts it for new designs. So just how good are we talking here? How close do these simulations get to reality? Well, in some of the best validated studies, the difference between what the computer predicts and what's actually measured in a real test is less than 5%. I mean, think about that. To predict the sheer chaos of an explosion with over 95% accuracy, that is just a mind-blowing level of precision. So once you have that kind of trust, that level of validated accuracy, you can start doing some amazing things and solving some really serious real-world problems. The applications for this tech are just vast, and in a lot of cases, truly life-saving. Of course, it's used to engineer stronger buildings and bridges that can withstand attacks. It helps design safer military vehicles and better blast doors. But it gets even more personal than that. Biomechanical models use these exact same principles to design better helmets to prevent traumatic brain injuries. It's used to make mining safer, to ensure gas pipelines are secure, and even to test how a drone might react to a nearby blast wave. But of course, the story doesn't end there. This field is moving fast, and the next huge leap forward is already happening, and it's all being driven by artificial intelligence. So what's the catch with all this amazing high-fidelity work? Well, there's a big one. Time. Running just a single one of these highly accurate simulations can tie up a supercomputer for hours, or days, sometimes even weeks. And that's a major bottleneck if you want to test, say, hundreds of different design ideas quickly. And this is where the real game changer comes in: artificial intelligence and machine learning. Instead of running that full, complex, time-consuming simulation every single time, you can train a neural network on the data from thousands of previous simulations. The AI literally learns the physics and the patterns, and then it can predict the outcome of a totally new design almost instantly. And the difference this makes? It's not just a little faster, it is a monumental shift in speed. We're talking about going from calculations that used to take a week of supercomputer time to getting an answer in seconds. This just blows the doors wide open for rapid-fire design and optimization, letting engineers test ideas that were just impossible to analyze before. And that really leaves us with this huge, exciting question. When the ability to test an idea and predict its outcome becomes virtually instantaneous, what happens? All those old barriers to innovation just start to crumble. It really makes you wonder, what new materials, what safer structures, what revolutionary protective gear can we dream up when the lab is limitless and the results arrive in the blink of an eye?